Yo, what's up everyone? Welcome to Oxidation Reduction Part 5. Today we're going to be talking about the Nernst equation. So usually you are given the standard cell potential. So in this table here, you're given the standard cell potential, and you can tell that it's going to be standard because you have this little degree sign on the top here. This textbook uses like a different symbol, but usually you have like E naught. Remember, standard conditions are going to be 1 molar, 1 atmosphere, and 25 degrees Celsius. But what if you wanted to find cell potentials at different conditions? Well, you'd use something known as the Nernst equation. So what does the Nernst equation look like? It's this. It's kind of big. So the cell potential equals the standard cell potential minus the gas constant times temperature over the number of electrons transferred times Faraday's constant times the natural log of the reaction quotient. There's two things here that I want to go over especially before we get into a example of this, and that's going to be Faraday's constant and the reaction quotient. So Faraday's constant is going to be the charge of 1 mole of electrons. So it's 96,485 coulombs per mole of electron. Pretty simple. It's just like a constant number. It's kind of very similar to like the gas constant or something like that. And next we have the reaction quotient, which is a measure of the relative amounts of reactants and products during any point in a reaction. And so if you had a reaction like A plus B is in equilibrium with C and D, the reaction quotient would look something like this. And you'll notice that it's very, very similar to the equilibrium constant, but the reaction quotient can be measured at any time, while the equilibrium constant can only be measured at equilibrium. So yeah, that's like the really big difference here. The reaction quotient you can measure at any time, but the equilibrium constant you have to measure at equilibrium. So let's look at a little example problem of this. Find the cell potential of a galvanic cell based on the following reduction half reactions at 25 degrees Celsius. And we're given the half reactions, and we're also given um, certain concentrations of our reactants. Remember, E cell is just E cathode minus E anode. And these are all standards, obviously. And so if we have a galvanic cell here, then our E cell value has to be positive. And the only way that happens is if the lead is the cathode and the CD is the anode. Okay, so our E cell here is going to be negative 0.126 minus 0.403. So our E cell here is going to be 0.277. And now we can find out what our overall reaction is. Remember, at the anode is where oxidation occurs. Oxidation involves increasing the charge. So really, we would have cadmium turning into cadmium 2 plus 2 electrons. And at the cathode, you would have just the normal reduction reaction. So lead 2 plus 2 electrons turning into lead. And so our overall reaction here would be cadmium solid plus lead ions turned to cadmium 2 plus lead solid. Okay, so I cleared some stuff up. And so what is the Nernst equation? Well, remember, E is E standard minus RT over NF times the natural log of Q. So let's start filling this information in. We know that our E cell value is our standard E cell value is gonna be 0.277 minus R, so 8.3145 times temperature, which is 298 Kelvin, which is 25 degrees Celsius as we're given over here, over N. So N is the number of electrons transferred during the whole process. And you'll notice here that the number of electrons is 2. So 2 times Faraday's constant, which is 96,485. And then we have the natural log of Q. Now, the Q value that we want here is going to be the concentration of the products over the concentration of the reactants. So it's going to be the concentration of the cadmium 2 plus over the concentration of the lead 2 plus, because remember, solids are never involved in our equilibrium expressions like that. So cadmium has a concentration of 0.02, and lead has a concentration of 0.2. So our Q value here is going to equal 0.1. So if we plug that in, all we have to do now is just solve this monstrous problem here. So our E value is going to come out to about 0.30, and it's going to be in volts. And that's basically the answer. So again, it's just knowing what information you're given and plugging it into the equation to find out what information you need. And so on the test, usually you have three other expressions here that are really helpful. So the standard cell potential is going to equal RT over NF times the natural log of K, which in this case is the equilibrium constant, not the reaction quotient. You also have some thermodynamics types of equations that you might need to use sometimes. And this diagram that I stole here kind of explains this relationship in this triangular fashion. Okay, so let's do a practice problem. What is the KSB of CaOH2 at 298 Kelvin? Now, for the KSB of CaOH, remember K is just the dissociation constant. The equation that we really want here is CaOH dissociating into Ca and 2OH minus ions. And the only combination of half reactions that work here, of these two half reactions that were given here, is if this one right here was the anode and this one right here was the cathode. I won't show how that works, but essentially if you just flip one of these reactions and you just look at which combination of half reactions produces this equation right here, you'll realize that the top one is the anode and the bottom one is the cathode. And so we can, using that information, we can find our standard E cell value. So remember, E cell is just cathode minus anode, so negative 3.02 minus 2.87. That comes out to about 0.15, negative 0.15. And so now you might wonder, what do we do with this information since we know we want to find K? Well, one of the equations that we know of is this one right here. This top equation right here. This will help us because remember, we have our standard E cell, we know R, we know T, we know N, we know F, and we need to find the equilibrium constant. So let's just write that down here. So E standard is going to be RT over NF times the natural log of K. And so now we can start to plug information in. So negative 0.15 equals the gas constant, which is 8.3145, times the temperature, which is 298 Kelvin, over N. The amount of electrons being transferred here is 2. So our N value is 2 times Faraday's constant, which is 96,485. And then all this is times the natural log of K. All we would have to do at this point is solve for K. And you can do that just by manipulating some of these numbers. And you'll realize that K is going to be about 8.4 times 10 to the negative 6th, which is answer choice C. And that is, in fact, the right answer. So I guess the big thing here is knowing which one is the anode and which one is the cathode. You can mess around with combinations of flipping maybe the top one and then keeping the bottom one and seeing if that matches up, and just mess around until you get that the right reaction, and you'll notice that the top one is the anode, the bottom one is the cathode. You can use that to find the standard E cell, and then you can just plug your information into one of these modified versions of the Nernst equations to find that your K is 8.4 times 10 to the negative 6th. On the actual USNCO, the test makers love these three equations. Usually you won't find the standard equation, which is this one right here, but you'll find those three modified equations pretty frequently. So make sure you know what these are and you're comfortable using them in actual problems. Other than that, that's basically it for Nernst equation. I hope you learned something, and I hope to see you for the next video. Thank you for watching.